Good afternoon, students. Today we are going to discuss the magnetic torque and momentum. In the last lecture, we have seen the calculation of the magnetic force for the external magnetic fields. There are different ways by which we can calculate the magnetic force due to the external magnetic fields, which we have discussed in the last class. Today we are going to discuss the magnetic torque and the moment, or we can say the magnetic moment. So to find out the magnetic torque and the moment, first we are going to consider a current loop, and this current loop is placed in an external magnetic field. When the current loop is placed in external magnetic field, the current loop will experience a force. Due to that, a magnetic torque will generate. Now, for that, we have considered this diagram. Here you can see that a rectangular current loop A, B, C, D, this current loop is placed in an external magnetic field B. When it placed in an external magnetic field, it experiences a force which tends to rotate that rectangular loop. So first we are going to understand what is the magnetic torque. Here the definition of the magnetic torque is given by this red line. You can see that the torque T, or the mechanical moment of force on the loop, is the vector product of the force and the moment arm R. So mathematically we can write that the magnetic torque T equals to R cross F, and its unit is Newton meter. Now suppose this loop has the length L from B to C and the width from A to B is W, and this current loop is placed in an external magnetic field B, which is uniform in nature. Now from this diagram you can see that the length AB and CD is parallel to the magnetic field. Therefore, no force will exert on these two sides of this loop. But the BC length and AD length, these two sides of the rectangular loop, is perpendicular to the external magnetic field. For that, a force will exert on this current loop. So we can find out from this the calculation of the force due to the external magnetic field on this current carrying conductor or current carrying loop. To calculate this, you see that the force F equals to I dl. Here we have considered a small length dl in this loop. So from B to C, it will be force F equals to I, capital I, that means the current flowing through the loop I, line integral of dl cross B, and from C to D it will be 0. From D to A it will be again the I, line integral of dl cross B, and from A to B it will be 0. So finally what we get, and also we can see that this dotted line is along the z axis. So dl length in this condition, we can consider this dl length is in the z axis. That is why we have considered that instead of this vector dl, the dz, that is the magnitude along the direction of az, similarly here also dz az. Now again, if you look at the diagram, that if you start from B to C, so we can say from 0 to L, and if we move from D to A, then it will be L to 0. So that is why the limit is considered 0 to L, and in the second case that is L to 0. So this term is we have considered, that is I integration of 0 to L dz az cross B, we have considered is F0. Similarly, from 0 to L if we consider, we will get one force, the magnitude of that force will be same as the previous one, but the direction will be different. So we will get minus of F0. So the total force on that current loop will be equals to 0. Here, if we want to find out the magnitude of F0, then from this equation we can find out that is I B into L. dl, if you integrate, you will find out the total length L. So I B L, because B is the uniform. B is the uniform magnetic field. So finally, from this expression 24.2, we can find that as a whole, no force is exerted on the loop. However, the force F0 and minus F0 act at different points on the loop, thereby creating a couple. So here you can see that the A to D length has the force which is upward direction, and from B to C the force it is in the opposite direction, is a downward direction. So due to these two forces, although the magnitude are same but the direction is different, that is why this current loop will rotate, and for that we will get the magnetic torque, or we can say it will create a couple. Now the one important point is that here is that if the normal to the plane, here you can see that the magnetic field is in this direction, suppose it is in this direction, and the magnetic, that is the current loop is placed parallel to the magnetic field. Now we are considering the plane which is perpendicular to the loop. So the normal to the loop plane, here if the normal to the plane of the loop makes an angle alpha with B, then the torque on the loop is, that is the magnitude of T, equals to the force, that is the magnitude of force, into the W sine alpha. Here the calculation of F is given in the right hand side. You can see that the total calculation is given, IBL, which is written here. That calculation you can find out that F equals to IBL. Now the magnitude of the torque, that is equals to F naught mod of F naught W sine alpha. So here from that we can find out the T equals to IBL W sine alpha. Now if we consider this L, that LW, L is the length, W is the width of the current loop, so that can be considered as the area. So here area is considered as S. So T equals to I BS sine alpha. Now this term I into S, this term is defined by one variable, that is M. This M, which is equals to Is, and its direction will be the normal direction to the current, the area of the loop, that means the plane of the loop, then M equals to ISN. Here this M is called the magnetic dipole moment, and it is in ampere per meter square. And N is the unit normal vector to the plane of the loop, and its direction is determined by the right hand rule. Fingers in the direction of the current, then the thumb along the direction of N. Now we can define the magnetic dipole moment. The magnetic dipole moment is the product of the current and the area of the loop. Its direction is normal to the loop. So from this equation 24.5 we can define the magnetic dipole moment. So after finding the magnetic dipole moment M, the torque can be represented in terms of the magnetic dipole moment and the magnetic flux density. Here if you put the equation 24.5 and 24.4 in this expression, you can see that we will have that T equals to M cross B. But here how we are getting? Here you see that M equals to ISN. So we can say IS into B into sine alpha. Here S is the LW. So we can write the torque T equals to M cross B. Now the equation of the torque, that is 24.6, is derived for a rectangular loop, but this expression which we have obtained by using rectangular loop, it is generally applicable in determining the torque on a loop, on a planar loop, if any arbitrary shape. That means the loop shape will be, if the loop shape is arbitrary in nature, we can use that calculation, but the loop must be planar or plane. Okay. So now the only limitation is that the magnetic field must be uniform. So this calculation is valid only for the magnetic field is uniform, and also it should be noted that the torque is in the direction of the axis of rotation, which we have seen in the case of the diagram, that the torque is in the direction of the axis of rotation, and it is directed with the aim of reducing alpha, so that M, this is magnetic dipole moment, and B are in the same direction. So in an equilibrium position, that means when the magnetic dipole moment and B, that is the magnetic flux density, are in same direction, the loop will be in perpendicular to the magnetic field, and the torque will be 0 as well as the sum of the force on the loop. So that is all about the magnetic torque and moment. Now we are going to see the magnetic dipole. A magnetic dipole we can consider as, we are going to see that what is magnetic dipole. For that we have considered that we want to find out the magnetic flux density B at this point P. Here you can see that this diagram, the point P where we want to find out the magnetic flux density B, and the point P has the coordinate r, theta, phi. That means this coordinate which we have considered is spherical coordinate system. In this coordinate system, we have considered a current loop, and this current loop is placed in the xy plane or z equals to 0 plane, and through this current loop the current I is flowing. So whenever the current I is flowing through the current loop, we can find out that the magnetic vector potential at this point P. If we can calculate the magnetic vector potential at this point P, we can find out easily the magnetic flux density at this point. So for that we have considered a small length dl, and for this small length dl we have the magnetic vector potential A by this expression, that is 24.7, which we have derived earlier. For a current carrying conductor, what will be the magnetic vector potential? So that expression we have used here, that A equals to the closed line integral mu naught I dl by 4 pi r. Now if this observation point is far away from this current loop, so in this case this r, that is the distance vector r, will be very larger than the radius of this current loop. So here if r is very greater than a, the loop appears small at the observation point. When the loop appears very small at the from the observation point, then we have only the phi component, and when the phi component is present, theta and r component is 0, then the magnetic vector potential A can be written as mu naught I pi square sin theta by 4 pi r square A phi. Now you see that here this I pi square is the area, I into the area, that is we have seen earlier. So this one can be written as in the form of magnetic dipole moment. So A equals to mu naught m cross air by 4 pi r square. Here how we are getting this one? M equals to I pi square in the direction of Az, and the magnetic moment of the loop, and Az cross air will be equals to sin theta A phi. Now whenever we got the expression A, if you look at this expression 24.8, then if you put that expression A in this expression, because we have derived earlier the relationship between the magnetic vector potential and the magnetic flux density, that is B equals to grad cross A. If you put here A and if you calculate this term B equals to grad cross A, you will find out the B, magnetic flux density B, that is equals to mu naught m by 4 pi r cube into twice of cos theta A plus sin theta A theta. Now we are going to look at this equation 24.9 and 24.10, and we are going to compare these two equations with the equations which we have derived in the case of electrostatics. In the case of electrostatics, we have derived the potential V, which is equals to P dot AR by 4 pi epsilon naught R square. So if you look at the expression 24.9, we are going to compare this expression with the expression V. Here you see that P is the the dipole moment due to the electrostatic field. So here P is replaced by M, that is the magnetic dipole moment. Dot is replaced by cross. Here is same, divided by 4 pi, same. Here epsilon naught is given. So in the case of magnetostatic fields, it will be mu naught. So mu naught is given in this expression, mu naught m cross AR by 4 pi r square. So that is comparable. Now again we have seen earlier in the case of electrostatic that E equals to P by 4 pi epsilon naught r cube into twice of cos theta AR plus sin theta A theta. You see that this expression is also similar to the expression which we have derived now. So in this way we can say that it can be therefore it can be said that the current loop can be considered as the magnetic dipole. The magnetic flux lines B due to the magnetic dipole are similar to the electric field lines due to an electric dipole. By pictorial view, we can also understand that a current loop can be considered as the magnetic dipole. For that, you consider these two diagrams. Here, in the right hand side of this diagram, a magnetic bar is given and the magnetic flux lines are coming out from the north pole and it is going in to the south pole. Similarly, if you consider a current loop and current is flowing in this direction, the current loop and through which the current is flowing in this direction, so we can have the magnetic flux or magnetic field lines that is similar to the magnetic field lines produced by a magnetic bar. So we can say the current loop as a magnetic bar or a magnetic dipole. Now if we consider or if we take a magnetic bar and also if we consider the Qm is an isolated magnetic charge, although an isolated magnetic charge cannot be present in real life, but here for our understanding we are considering, suppose Qm is an isolated magnetic pole, or you can say it is the pole strength, and L is the bar length, then the bar has the dipole moment Qm into L. Here in this diagram you can understand the north pole. Here the pole strength we are considering Qm and the bar has the length L, which is placed in the external magnetic field. For that, a force will act on this north pole and the south pole, and that will be in the opposite direction. For that, the torque will produce. Okay, now notice that the Qm does exist, however it does not exist without an associated minus Qm. So when the bar is in uniform magnetic field B, it experiences a torque, which I have discussed now, that the force will act in opposite direction. For that, the torque will generate. So this torque can be calculated by the expression which we have derived, that is M cross B. Here magnetic dipole moment M is replaced by Qm into L cross B. So where L is directed from south pole to the north pole, the torque tends to align the bar with the external magnetic field. That means this torque will try to align the magnetic bar with the direction of the external magnetic field. Now the force acting on the magnetic pole, any pole you can consider, if you consider the north pole, then the force equals to the pole strength into the external magnetic field B. Therefore, for both the cases, that is for both the magnetic poles, a small current and a bar magnet produce the magnetic dipoles. So we can say the magnetic dipole, that means the current loop, a current loop can be considered as the magnetic dipole because it has the characteristics of a magnetic bar which is having two poles. Therefore, we can say the torque T equals to QMLB, or that is equals to ISB. So here QML equals to IS. So this is the proof that a current loop, a small current loop, can be considered as a magnetic dipole. So thank you very much, students, for today's lecture, for attending the today's lecture. In the next lecture, we will study the uh, boundary conditions of the magnetic field. Thank you very much for attending the class.